Honored to be here with Dexter, magician on the soldering iron and creator of bunches of PCBs to hack all kinds of embedded systems. I'm Carsten. We both work at the same little research lab in Berlin where we take apart pretty much any hardware put in front of us, including the occasional silicon chip, focus of today's talk. We want to not introduce any cutting-edge hacks, neither break something that wasn't broken before, but instead give an introductory talk to chip hacking, make you understand what other, mostly very well-equipped labs have been doing and are continuing to do as one focus of today's talk. The second focus is going to be the introduction of a tool set to do microchip analysis on the cheap. Set of tools that Dexter has been putting together over the last couple of months that will hopefully enable some of you to join the surprisingly small group of people who do analyze silicon chips at the lowest levels. We want to draw attention to microchip analysis, mostly because we're observing a trend that more and more functionality is being hidden away from users inside hardware, basically reverting lots of progress that the free and open software movement has made in opening devices to creative users. Those devices are now being locked down further and further through secrets hiding in chips, and people have a harder and harder time understanding how these protection mechanisms work. They have a harder time circumventing them to deploy their creative extensions, and especially have a harder time analyzing these devices for the unintentional vulnerability or intentional backdoor. So there's more research and analysis, and more people with skills and tools to execute this analysis needed to, again, open hardware to the level that everybody should be used to bring back the control to whoever purchased the device rather than leaving the control to whoever manufactured the device. Right? Applications that are chip-enabled or chip-secured these days range from really any hardware, appliances in the household, smartphones, tablets, computers now with secure boot, all the way to maybe cars. And with the exception of cars, perhaps, all of these devices should be customizable and should be extensible. Basically, a tool is missing that would be the equivalent to decompiler and disassembly chain in software, where anybody is free to look at a piece of software, derive its functionality, check for backdoors, and change the software as they wish. Hardware hackers have, over the last couple of years, created a bunch of tools to do this level of analysis on PCB boards, basically where different chips communicate with one another and where functionality needs to be derived to understand how to extend the hardware as such. But those efforts are increasingly being defeated by more chip integration, by more and more periphery moving inside a single silicon die and then locking out the analysts who may have so far always succeeded in finding, for instance, a JTAG or other debug port to extract software and then look at the software, nonetheless change it perhaps even. Right? So we want to introduce some methodology, tools, and a few things for you to try at home to look into those chips and start chasing the software where it's currently hiding and make sure to keep whoever created the software honest and to keep the hardware it's deployed in as open as possible. As I said earlier, this is an introductory talk to some research that has already happened in a lot of cases. It's also a complementary talk to another line of research presented at a bunch of the congresses. Those were focused on extracting functionality from chip, basically the equivalent to static software analysis. Where you take a chip, take it apart, look at its different parts, reason about how these different parts interact, and then derive, for instance, a secret cryptographic cipher. That's the one line of research that Starbuck was fundamentally pushing, and that's building up on a tool set by Nitram, the DGate software. There's a second line of research, mostly driven by analysis labs. The most prominent public voice of which, of course, is Kristianowski from FlyLogic, but a bunch of other labs also do this more in secret. These labs execute the equivalent to dynamic analysis, where the chip is kept alive and kept running and is being observed as it executes certain things with the goal of extracting its software or perhaps changing its software, but more often just extracting the software, including certain secrets you need to enable extra functionality or understand some secret protocol. The camp last year saw a confluence of those two, where static analysis led to an easy way of extracting memory from a smart card. But other than that, those two worlds have been pretty much separate. What has been missing so far, at least from my perspective, is an explanation on how these failure analysis labs actually go about extracting the code, and that's the missing piece we want to add today. In addition, we want to show how their tools can be scaled down significantly to then apply to at least some older chips and being able to analyze those. To be presented in 3 acts. First, some basic methodology and kind of the theoretical foundation behind these attacks. Dexter will then explain his setup for doing very low-cost analysis, and I'll add at the end a discussion on how professional laboratories with much better equipment maintain an arms race with the chip manufacturers and what they are currently doing in terms of attacks and defenses. Sounds good so far? All right, then. To understand how you exploit a chip, let's first create a mental model of how a chip, any chip really, executes, and where the perfect sweet spot would be to intercepting secret information. A chip, at least to me, is composed of 2 main components. There's the memory that stores a program or data, secrets for instance, as well as a CPU that can execute one little segment of the memory at a time. So those two interact in that a memory instruction is fetched, an instruction is fetched from memory and stored in what would be an input buffer into the CPU. It's called the instruction latch. And then from this instruction latch, it's flowing into the CPU, triggering all kinds of little functions. Depending on what instruction it is, it will do something mathematical, or it will move data around from registers and so forth. And this instruction will, in almost all cases of instructions, then increment the program counter for the memory then to provide the next instruction, and that gets executed, and the program counter is once again incremented and so forth. So there's this back and forth between the CPU and the memory. There are certain instructions, and very few indeed, that change this flow by not just incrementing the program counter to the next memory address, but rather overriding it with something completely different. So a jump instruction would override it with a register content, and for instance, a return instruction would override it with the top of the stack. So take a completely different address, write it in the program counter, provide this as the address into the memory, and the next instruction being fetched is somewhere completely different. Of course, those are needed to make any interesting kind of program, otherwise it would just execute singularly all through the memory, right? Let's assume now, and Dexter will explain how that's actually happening. Let's assume that we could intercept data flowing on these data bus wires. They're pretty long wires connecting pretty disjunct parts of the chip, so there's a good chance that somehow these wires can be tapped with little needles. Now, if we did put a needle on one of these bits, what would we actually see? boot up the chip, would see it go through some kind of self-test routine. It would maybe write things to memory, read them back, check that the memories are working. It would set up some internal peripheries. It may set up memory maps, the MMU, and so forth. And then it would start executing the actual program. And it could be as simple as going through an infinite loop until somebody provides the right PIN number, and only then executing the actual program. So on this data bus wire, we may not see anything interesting as far as the program is concerned. Or it may be a TV setup, smart card, where it now waits for some server communication, some data sent through the satellite. It would decrypt that data and then work its program. So in almost all cases, it needs external simulation to do anything interesting, and oftentimes even external secrets that in an analysis setting you usually don't have. So you only see very small parts of this program. Why is that? Of course, because of these flow-altering instructions that maintain a little loop around something non-interesting, preventing the program from ever going anywhere interesting. So an attacker's goal now would be to disable all these instructions that make it jump around, and rather prefer instructions that singularly increment the program counter and walk through memory, as Kristanovsky says. And there's two ways of achieving that, at the least two ways, two kind of generic ways. So again, we have this instruction latch that's actually just a series of flip-flops that's being populated from the memory with instructions. And whenever it receives a trigger, it's usually referred to as a clock, but really it isn't a clock. It's not symmetric, as it has this different pauses depending on how long instructions execute. So basically it receives a trigger whenever the CPU asks for a new instruction. It's still called a clock. And only then the instruction is moved from the input to the output, kind of like a triggered conveyor belt that keeps the output static until it receives this trigger, and whenever the trigger is received, moves whatever currently is at the input to the output. Right? Now let's assume there's a NOP instruction executing right now. A NOP instruction does very, very little. In fact, only two things. So it doesn't have any logic. You know NOP, no operation, right? It increments the program counter because it needs to move on to the next instruction, waits a little while for the memory to be able to populate the new instruction into this input buffer, and then triggers that the NOP instruction is executed. Is moved through this conveyor belt, right? And then whatever new instruction is in also executes its CPU logic. Let's assume now for a second that we could prevent the trigger from reaching the latch. So now the NOP instruction executes. It increments its program counter. Some other instruction is being moved to the input of the latch, but the trigger is never received. So the CPU will assume that it triggered, and it will fetch the next instruction on the output of this latch, which still is the NOP instruction. And it will increment the program counter once again. And it will do this ad infinitum, walking through the entire memory. Right? So one way of making this chip go linearly through the memory, independent of whether you actually have the access rights, whether you typed in the right PIN number, whether you provided the right server communication. One way of doing this is by holding this clock input stable and preventing the triggers. Right? So this is an attack now that only takes two needles, one for listening to one of these data buses, and the other for keeping the clock in a stable state after a certain instruction is fetched. Now this first needle will have to then, after intercepting the first bit, intercept the second bit, and so forth. And then you puzzle together these different pieces of the instruction. And this, in almost all architectures, allows you to make the chip, smart card, whatever you have, spill out its entire memory content. In some cases, these clock lines are pretty well hidden, or there's even protections on them where the chip notices when the trigger is not being populated. So people come up with alternative ways of doing this. One very elegant one, I think, that works against some instruction sets is to change the instructions as such. So you allow it to propagate through the latch, but you keep one bit stably 0, 1, depending on the architecture and which bit it is, to never allow any flow-altering instructions. So in the ARM architecture, all these instructions have a certain bit set, and if you reverse that bit, it will always be some other instruction, oftentimes an illegal instruction. They don't exist, but the CPU kind of moves on, increments the program counter nonetheless, and walks through memory. Doesn't really do anything meaningful anymore other than providing all that data you want. Right? There's a couple other ways on other smart cards, especially how to force this, but that's the basic idea. Force the chip to execute meaningless instructions and never jump anywhere. Right? That's the basic idea. It gets a little bit more complicated in cases where memory management is involved, because this, of course, will only ever walk through the memory currently mapped. And if there's other memory segments, this attack may need to be executed several times when the right portions of the memory are mapped in. Right? So good so far. So Dexter is now going to explain how this putting needles on the chip business actually works and what tools are involved in that. The attack he's describing is slightly different in that we don't actually have to tap the data bus and all that on the chip he chose as an example, but the same principle applies. You override a bit, in this case a fuse bit, and the chip loses its protection capabilities. Right?
Okay, let's start. This is the basic setup we currently have in use. I actually have constructed this out of off-the-shelf components and some self-made components as well. The most eye-catching part you can see is the microscope itself. You see the microscope head mounted to a girder. It's completely static and not movable. It's a specialized microscope. It's specialized for the probing task.
It's specialized in that it has a large working distance, so the microscope is pretty far from what it's looking at.
Yeah, it's about the working distance. The objectives are actually what is specialized. The rest is a normal thing here. And you also might notice this large XY stage. It basically consists of a large steel plate. Steel because it's magnetic, and our micropositioners you see on the left there has also a magnetic base, and it's also very handy because you can stick with little tiny magnets. You can hold a target and micropositioner and other things in place. Yeah, the micropositioner itself is a professional variant. Better show it here on the display with the mouse. This is the micropositioner, and it has these green knobs to move it around in X, Y, and Z direction. This one can be bought for about €300, but the prices are varying from €300 to maybe €3,000. You can spend basically infinite money on that. But for €300, you get a good entry-level unit. The unit itself is extended, where's the mouse here, with an arm. On the end of the arm, there's a little holder that holds the needle in place, and the needle, when needle touches the chip surface, it directly touches the tiny wire trace directly on the chip, and the other end of the needle is connected to a buffer. This buffer has basically the task to amplify the weak signals on the chips. The tiny transistors you find on chips are only made to drive these tiny traces, And if you hook up a large wire, then the stray capacity and the input capacity of the measurement equipment may disturb the chip functionality. That is why you need a buffer here. And yeah. And also, we equip the arms. When you buy a micropositioner, the arm is usually it's usually a piece of metal with maybe some screw to hold something in place. That is not really suitable. So I extended this arm with with 2 pieces of PCB material, and I also added 2 screws to clamp this needle into that, and it's fully insulated from the rest of the setup. That is actually very important. The needle itself, it's made of tungsten. You might know tungsten is not solderable, so we have a removable connection here. You can just pick that. Oh, it's fun. Yeah. Okay. Yeah, it's removable. It's meant to be removable, and it's glued everything in epoxy. After that, a measurement amplifier is bringing everything to TTL levels to hook up a logic analyzer. There's also something important what we need. Of course we need a target. In our case, it's a PIC 12C508A. It's a very old microcontroller. It's a UV erasable microcontroller. If you buy it in plastic package, then it's of course not erasable. Then it's an OTP version, but you can buy it in ceramic casing. It has a copy protection fuse. It's one fuse that if you program it, it's EEPROM memory, 1-bit EEPROM memory. You program it, and then the controller refuses the readback functionality. You cannot read back the code anymore. It's already hacked. Mostly when you hack one of these devices, you would use a UV attack. UV light erases the microcontroller, including the fuse, but when you cover the EEPROM memory, when you find it on the chip and you cover it with paint, then it cannot be erased anymore, but the fuse are getting erased, and so you can unlock the chip and read back its contents. The cables you see here are running down to a programmer. The red little thingy is an EEPROM programmer. That is because we need something to stimulate the chip. Whenever you probe something, not only in this case, when you probe something, you have to set the chip in function. You have to give it an environment where it can work. Basically, controlled environment. If you do the thing that Carsten mentioned, then you also have to take care about clock stability and synchronizing things. Yeah. In this case, the chip's already opened. Opening chips is not that easy, but it's doable, even for an hobbyist. On the left thing, it's quite funny. I opened it with a screwdriver by mouse. Here's the mouse. Here's the chip, and here's the screwdriver. I opened it by prying it. You just apply the screwdriver on the joint where the ceramic package is. It's joined together. It has a top and a bottom part, and you knock it softly with the screwdriver, and the package top is flipping off. And if you are very careful with that, and if you have luck, then all the contact legs are kept intact, hopefully. But if one leg loses, that happened, then I just use another micropositioner to replace that. Yeah. On the other side, we have a controller that is etched. It has been etched with fuming nitric acid. And the good thing about fuming nitric acid is that it leaves the bonding wires and the chip itself fully intact. Bonding wires are the tiny little wires that connect the pads, the bonding pads on the chip itself with the outer legs. It's a connection to the outside. And it's important to have that because you want to hook up your working environment, your programmers, and everything that is needed to make the chip working. Yeah, in this case, we didn't do that by ourselves because fuming nitric acid is very, very toxic. Yeah, the fumes are also very toxic, and it's not available to the average hobbyist because of these terrorist thingies. Yeah, some people used to build bombs with that. Anyway, I can give you I can tell you how it is done. You just heat up the chip, apply a drop of this fuming nitric acid, it adds etch-slippage, then you rinse it in acetone, and you repeat the process over and over again until the result is good. We also have another method that is not depicted here, but you can use colophonium. That is mentioned in previous talks before. You just boil the chip in colophonium for about an hour, and then you rinse it in acetone. And then the problem is about this: you lose all the bonding wires, and you have to replace them somehow after that. In some cases, if you only need ground and VCC for the chip and maybe a clock line, then it's okay. Then you can use other micropositioners to compensate it. But for the normal hobbyist, it's not really feasible. You can acquire a bonding station, then you're out of trouble, but this would increase the costs very high, and it's not feasible for the average hobbyist.
What's important to mention is that professional labs will etch open chips like depicted on the right side for about $50. So that shouldn't be a hurdle, even if you don't want to touch the acids themselves.
Yeah, we did it so. We sent it in and paid $50 per chip, and that is what we got back. When the chip is open, we have to contact these tiny little traces somehow. Unfortunately, they are protected with a layer of basically glass. The chip is consisting mostly of glass. Of course, it all is built up on a silicon wafer, but then layer by layer is applied in the manufacturing process, and after that it's sealed with a passivation layer. It's silicon dioxide, and it protects it from oxidizing. And there's methods of choice for the average hobbyist again. You can penetrate the passivation layer using a scratching technique. And how it works is very easy. You put a needle right next to the trace, not onto, right next to because on non-planarized chips, on non-planarized chips, there's not taken care in any way to balance these hollows and hills which building up on the chip, and you have these hill of silicium dioxide on it, and if you move it forward and back, you stress the material, and at one point it will break, and then it appears to look like this in the end when it's broken, and then the trace is ready to get contacted with the needle. In most cases, you can just move the needle back, and then it's contacted. Okay. There's also another option available. When you want to professionalize yourself, you can add a laser to your microscope. This is a very, very expensive method because laser is a very costly installation. And also the objectives have to be corrected for certain wavelengths. You get objectives for infrared light. They are optimized for infrared light or for UV light. And these optics are very, very expensive. So if you acquire a laser, you have nothing in the beginning. You have to also acquire all these optics. Yeah, it's completely not affordable for hobbyists, even because of these special things you need. The handling is sometimes a bit difficult because you might, if handling is not properly handled, maybe then you might destroy structures you want to destroy. The same applies to scratching as well. If you make a mistake, you might destroy structures next to it, and then you lose maybe you lose the chip. In the beginning, this often happens, but if you have some practice, then you get better and better and better, and yeah, then it's no problem anymore. Yeah, one word to scratching again. It's only feasible for traces that are not in a dense area of the chip. If the traces are running very dense, then you have no space to perform this. Then the laser is the ideal choice for you. Okay, let's now come over for the to the fun part. We want to actually use our probing station to exploit a real existing chip. Yeah, every kind of these attacks starts with an imaging process, because you want to know your target. You want to have an overview image of it. This is not done with the microscope you've seen before. It's done with a much cheaper microscope which is optimized for imaging. I think it's €2,000, about €2,000 for microscopes that is capable to produce such images. After I've done imaging, you can try to analyze the structures you see. In our case, we have focused on the fuses. It's not the case that we didn't try to do the linear readout thing Carsten mentioned, but yeah, it's not visible on the image. But here, I didn't found any point where I could tap the output lines from the EEPROM. So I focused on the fuses. And it's quite surprising. The fuses are quite large structures on the chip. You might expect that fuses are a tiny structure, should be a tiny structure on the chip, like an average gate or something. But yeah, they are actually very large. Here you see them. These are the fuses. And you can identify fuses by basically applying two methods. One easy way is you just take a bit of paint and cover the chip, and then you check if you can erase it. And when you cannot erase the fuses anymore, then you know that the fuses must be underneath the part that you have previously covered with paint. I did so, and I could prove that the fuses are right in this area here, not in this. I expected before accidentally. Okay, so another idea to find fuses and memories on the chip is to look where the VPP voltage is coming from. In this case, well, easy. It comes from an outside pin, and yeah, just trace the VPP. It's not visible. It comes from this pin. I traced it down. Here's the red line where the VPP line goes, and it ends up here, right where the fuses are. Because, you know, fuses are 1-bit memory, EEPROM, and EEPROM means programming voltage. So once you know where the fuses are, you want to find the output lines of the fuse to overdrive. Okay, it is when you reverse engineer chips, especially it's mentioned in the talks before, we have this polishing thing. That is what I didn't here. I didn't polish here. I just took my overview image and looked what traces could be the output lines of the fuses. And then I probed these ones. And it was an easy setup. I just erased the chip, probed the line, see if it's a constant level, high in this case. EEPROM memory is outputs normally in high level when it's unprogrammed. And then I programmed the certain fuse. And when it dropped on the oscilloscope screen, I see it was a 0 level in the end. Then I have it's pretty capable that this is the fuse I'm looking for, and that is what I done. Yeah, it turned out to be not that easy because the output line of the EEPROM is running in one of the deeper layer, but it still could be found. And this image here is taken by Kristanovsky, but I received it after I found the fuse, so I really can confirm that I found it really by myself. This is the view through the microscope. This is what the attacker sees. The image is a bit blurry. It's taken with not that professional camera. The human eye sees a much better image, but it's you see the needle. The needle here is a blurry shadow. You always see the shadows that the needle is throwing on the ship's surface. And it taps this wire here. This wire coming down from here to here, and here's the tap. This is also done using scratching. I didn't use the laser here. It worked even though if it was in one of the deeper layers. This was actually the only point where I could penetrate this line. On all other places, it was covered with top metal. Yeah. When you get the needle in position, some folks prefer TTL buffers as buffer circuit. I prefer an operational amplifier in voltage follower mode because it's more transparent electrically. And to know if I'm in the right position, it's just easy. I look at the noise level of the needle, and when the needle is coming in contact with the chip surface and on any wire, hopefully at the right one, the noise level is dropping because the chip is grounded through the EEPROM programmer circuit. That is how, then I can know for sure that I have contact the chip and I can start my measurements. Yeah. So here, okay, you might think, yeah, using this expensive microscope, it's still expensive. Yeah, why we call it low-cost microprobing then? Yes, this is what I have at home. This is really low cost. This is my private microscope. Cost me about 2,000 euro. Feasible for a hobbyist. I really like it. It's very, very old. It's an old size vertival. What I did then is I enlarged the object table, and yeah, it was about 70 euro because I didn't want to ruin my original object table, so I got a new one, and it was about 70 euro. Yeah, and aluminium plate covered with a steel, with a thin steel tin. Because I wanted to be magnetic, because all the micropositioners in our setups are always magnetic based. Yeah. Okay. One word to the little tiny PCB here. See, this is the other end. Is the other part of my voltage of my measurement amplifier. It's all on a PCB which is capable to apply the voltage needed for the operational amplifier and the level shifting circuit and comparator circuit, all microcontrollable USB port and so on. And I will publish it under an open source license when it's finished. But if you are interested, you can ask me. Yeah, there's one major drawback we didn't talk about yet. The specialized optics we use on our microscope in the company, they have a larger lens on the bottom. On an imaging microscope, you have very, very tiny lenses at the end which are looking to the object itself. And on the specialized optics, it's different. It's larger, and the numerical apertures, which is basically which has an effect on the working distance, is also lower in the most case. On an imaging microscope, it's exactly the opposite, and that is because I have only a working distance of 2 millimeter here. But anyway, it's also possible to maneuverate the needle through this 2 millimeter gap down to the chip. And the experience was basically the same. It was a bit shaky, but anyway, it worked. And that's the important thing about it. It worked, and it is feasible for under 3,000 euros. That means that an average hobbyist can do microprobing in his basement. So yeah, that's it. That's my part is done now.
Yeah, applause indeed. That may very well be the cheapest probing setup so far, and I hope it's inspirational to a couple of you, especially those with microscopes already, to add in those remaining pieces and start probing some simple chips yourself. So this was a pretty simple chip. It didn't try to do much in terms of hardware security. It had logic level countermeasures that Dexter circumvented. So let's look for the remaining couple of minutes at how to overcome the restrictions of this setup with more professional setups. So this setup would run into two dead ends. First of all, chips get increasingly small in terms of feature size. So the structures you're trying to probe get smaller and smaller over time, and especially with the scratching, you don't really get through to these tiny structures anymore without destroying a bunch of other stuff on the chip. The second limitation is that some chips actively try to fight this kind of probing with defense structures, and those, of course, are built with setups like this in mind, and they are pretty effective against them. There is one tool, though, that gets around both these restrictions, and that's called a focused ion beam. It's a pretty ingenious tool. It shoots accelerated ions onto a surface, for instance, a chip surface, and in a normal mode, they just bounce off the chip, and depending on how they bounce, they are collected and then made into an image, basically like an electron microscope, where you shoot electrons, but in this case with ions. Same system applies. And images come out like this, where this is really the different ions having bounced off differently off this chip surface, and then being recognized as higher or lower. You can see a 3D structure here. Beyond the electron microscope, which could also have produced this image, it has certain active operation modes. If you accelerate the ions a little more, they don't just bounce off the surface, they actually shoot out atoms off the surface. So they destroy whatever you're looking at slowly, slowly. It's milling through the chip. And you can see how there are certain cuts in here where the FIB has already cut into the chip. Right? So that's the one active operation mode. The second operating mode is to put in these ionized gases certain other materials, for instance, platinum gas, and the platinum ions, they'll be thrown onto the surface and they stick wherever they touch the chip. So with these platinum ions, you can build up structures. And putting those together is really surgery on the chip. So what has been done here is, and this was done by Kristanovsky of FlyLogic. He milled in these boxes, the big boxes, and then built in a few more holes to see where on the chip he is exactly. For instance, this is a small cut that looks deeper down and sees the actual metal wires that are running probably 2 layers down from where he started. And one of these metal wires he was most interested in, I think it's this one, and he drilled right over here a small hole with the same technique, shooting ions and drilling down all the way to the metal. And this is similar to what the laser achieved earlier, but this hole is so tiny you can't possibly stick a needle in. So then he started throwing platinum at it and filled the hole with platinum, so it's conductive with the metal underneath. And to make it even more convenient for the needle, built this little ring, again, of platinum. So if you stick in a needle anywhere in this ring, it should connect to the metal underneath. Right? So this is enabling then for somebody like Dexter to just use the standard needles and get the data out of this chip. He did some cleanup then. You see these cuts. This is so that the two metal pieces are not actually connected, and a whole bunch of small other things. So this is really magic how these tools are operated. But you can imagine doing anything now with a chip, right? Even connecting different wires that are previously not connected. So you do edits on the circuit. That's what it's called. And this is actually why these tools exist in the first place, because chip manufacturers, as they build chips, do errors, right? First versions of the chips always are error-prone, and then they need to reroute some wires, they need to cut some wires, they need to create new ones, and these tools are coming out of these chip manufacturing facilities, but now they're also being used for, well, the euphemism is failure analysis, so trying to find exploits. The chip manufacturers know that, of course, and they try to prevent people from doing anything, scratching, lasering, fibbing to chips through active protection. And the most common and most wasteful, because it takes a whole metal layer, is called a mesh. So a mesh is a snake that runs all across the chip, and in fact, in most chips, several snakes kind of interleaved. And it measures whether the snake's beginning and end is connected before it executes anything interesting. So if you start drilling through this top layer to get to something interesting underneath, the chip notices that the snake now is broken and it will refuse to operate or even do more active alerting. And usually the mesh is tight enough so you can't get through in the middle. Some people try and succeed by fibbing very carefully, just in between two tracks, kind of cutting a little bit on the edges of both tracks and then cutting through, but that's really advanced. There are more generic counter-attacks against these meshes, though. So this chip, for instance, even has two active protection measures. To get to these latches we looked at earlier, the really interesting structures, you not only have to penetrate the mesh above, also this metal shield. Fortunately, this is not a mesh, so if you can just cut through. But again, if you try to do this with scratching, you'd mess up all kinds of stuff around it. So this also asks for a fib. Now, how do you defeat a mesh? So here's an example of mesh lines. And again, they're very, very tight, so hard to probe in between. You'd rather want to cut a little window in the middle to get to, for instance, the latch clock, but then have to make the mesh logic believe that the mesh hasn't been breached. Here's color-coded the connectivity of this mesh. So these snakes go, the purple one goes something like this, and the other colors interleave with it. And it will test whether the first purple is somehow connected to the last purple, but it doesn't have to go through the snake necessarily. So if you cut a window in the middle and you bridged a left purple with a right purple and the left yellow with a right yellow, it would still have connectivity. And again, the fib, with all its capabilities of cutting and then depositing platinum, can actually do this. This has been the most common attack against modern smart cards of the last years. People just figuring out how these mesh circuits are connected and then cutting windows in and bridging them. It's a couple more interesting, from my perspective, attacks, because this is simple, right? Like conceptually simple. It's just a lot of work finding where to cut and then actually executing it without destroying the chip. So the more interesting attacks to me are those that defeat the logic behind the mesh. For instance, one family of smart cards, what it does is, as soon as it notices that the mesh is breached, it will bulk erase the memory. So all secrets are being deleted. Right? And next time you power on the chip, it's worthless pretty much to the attacker. Programming, as Dexter said before, takes a certain voltage. Usually on these smart cards, it's not supplied externally. It's generated on the chip through charge pumps. But of course, these charge pumps can also, with the fib, be cut off from the memory. So even if a bulk erase circuit triggers, that doesn't necessarily, it will bulk erase if the voltage is missing. So if you cut the mesh and then also cut the supply voltage into the memory, that defense is defeated. Right? Some other chips is a different family, take a long time, and it's a magic to me why a chip can take so long thinking about whether the mesh is breached, but it takes a couple of thousand clock cycles to decide, yes, the mesh is breached. And that's enough to execute some part of the attack. Reset the chip, then execute the next part of the attack. So the logic is often easier to defeat than the whole fibbing business, especially as these become more interwoven or become three-dimensional, where you'd have to breach two different levels. But the arms race goes on. Up the sleeve of current and future smart cards are things like analog meshes, where the simple connect different lines that belong together attack is defeated through supplying an analog signal and then actually measuring the antenna capabilities of these lines. And that, of course, are changed through the edits. Other things that are already found in at least one smart card is redundant distribution of data, where you'd have to intercept the data in different places at the same time, basically defeat two different cores with the same attack at the same time, and those cores, they kind of help each other stay secure. It may sound wasteful because it doubles the resource footprint, but of course it's much less wasteful on the chip than adding a whole metal layer. So I like the idea. I'd like to see somebody look at it more closely, though. So the arms race goes on, and it has gone on to a point where only a few specific labs can now work on the most recent smart cards because of all these meshes and whatnot. One new idea is emerging currently, has been in the discussion for a couple of years. TU Berlin are the first who have been doing it academically very successfully, again with failure analysis rather than hacking in mind, but that may change. And the idea here is to approach the chip from the other side. So we're talking about the front side and the back side of a chip. So the front side is where all that glass and the metal is, and the back side is just a relatively large plate of silicon that gives the chip mostly stability. So it doesn't have to be this big functionally. And all attacks so far have focused on coming from the front side, then breaching the mesh. This is a mesh. You see all these metal wires here on metal 3, breaching the mesh somehow, and then drilling down to something on metal 2 or metal 1. Is this graph self-explanatory enough? So there's transistors on the bottom here, basically gates. And you can't see the transistors in this picture, actually, but you see all the connecting structures on different layers and how they are kind of in a three-dimensional circuit all tied together. So people come from the front side, breach all security, and then tap on some of these wires. But the exact same information, of course, is available at those transistors that generate them in the first place. So an idea now is to come from the back side and tap the transistors right away. This would really defeat all meshes by definition, because they are on the other side. There's actually no way of putting a mesh on the back side. There's really no logic, and the transistors have to be the lowest layer, and they have to carry the information somehow. It creates certain challenges around keeping the chip stable to operate as you drill through and thin the silicon too much, that the chip stops running stably to supply certain extra clocks and whatnot. But in the arms race, this seems the most promising approach so far. I'm just mentioning to make it clear that the chip manufacturers are far from winning the race. It's more innovation, of course, is always needed on both sides. But once this is available, I think the attackers again have the upper hand, mostly because chip manufacturers haven't seen it coming from this direction, and then all chips that shipped this year and the last couple of years are again vulnerable. So that was our brief rambling walk through the world of smart card and chip analysis. Hopefully this was inspiring enough for some of you with microscope or with $2,000 to spare and buying a microscope to pick up one and start probing some simple chips. Hopefully we can all can move forward this field and maintain the struggle with manufacturers and making the devices we pay money for our devices, right? And not allowing anybody to hide their software, secret algorithms and backdoors in hardware any longer. Well, thank you very much.
We have 6 more minutes for Q&A. So if you have any questions, please do line up behind the microphones over here, here, and here. And while you line up, we'll have 2 quick questions from our ISC people.
There was a question, I wonder which resolution for the microscope is advised.
What resolution is needed for the microscope? Is that a question? For the chip, we looked at resolution somewhere between 2 and 500 power would be more than sufficient. So not the most expensive microscopes are needed. The most you can ever get optically is a magnification of something like 1500. And that would be needed to breach chips of a feature size of down to something like 200 nanometer, right, to give you a couple of numbers. But it really depends much on the chip you're looking at.
Yeah, to the resolution, I can say physically a magnification over 1000 is not really possible. The images get blurry for magnifications that are any higher.
While you're leaving the room, please be a little bit more quiet. Thank you.
The second question was, Carsten, did you try this on latest EC cards with wireless payment activation?
Well, EC cards are usually pretty well-powered smart cards. In fact, in my opinion, much too well-powered smart cards. Their weaknesses are more on the protocol level. But yeah, the fibbing attacks would work against them with plenty of experience and a couple of months of work per chip. The simple attacks, no chance if you touch on actual smart cards like the one in banking cards.
Next question from the right-hand side room microphone.
I have 2 questions, one for Carsten and one for Dexter. Carsten first. If you go back 1 slide, my question is about the last slide. You are talking about backside fibbing here and chip thinning, and this being a new attack, but I heard about this when working at a chip manufacturer in 2005, I think it was, 2006 maybe. Mm-hmm. It's been around for a while. Why is this technology just now being...
Puzzling to me as well. So there are people who can pull this off. None of them are involved in security, though.
Yeah, they were not security people.
They will measure properties of transistors, analog properties, so much harder to execute analyses than just intercepting bus bits. But this hasn't been proven to work on a smart card with some security functionality, and it's about time that somebody does it.
Sure. And my other question was, I'm interested in some more technical details on the low-cost needle setups, the micropositioners, and what kind of needles do you need? Are there any special properties? Do you have to? Do I just take a sewing needle and sharpen it? How do I get to the fine point that I need for this work?
Yeah, I can answer this. I think the needles we used are called tungsten tips. I think I will find it when you search the net for that. It's basically a very, very simple needle. They come already sharpened in a case, and you pick one, and basically after you have used it a few times, they are worn. Then you throw it away. They come ready, and we just take them. And they are available. I think it's called tungsten tips. I don't know how sharp it is, but it's. I think I don't know its exact numerical value for the tip radius, but it's about the size of one of the traces you have seen. The tip is about the same size than one of these wire traces that the chip has.
Interesting. And what can you say about the micropositioners?
Micropositioners? What's the particular question on that?
I guess I'm asking for a longer a paper or how
please keep your questions short. We only have 1 more minute
So
left.
the micropositioners we just found online from some German guy in Texas. He constructed them himself. He ships them for $350, I think. They are for this type of chip all you'd ever need.
You also can try to look on online auctions for Wentworth or Signatone. You find in the US you find lots of cheap supplies from leftovers.
We have time for 1 more question from the left-hand side microphone.
Yeah, hello. I wonder that you use this scratching method. Wouldn't it be possible to use a piezo actor that gives a vibration to the probe?
I understand you want to do it like a dentist removing dirt from your teeth. We thought about that, but scratching is it's more feasible. I don't know how to attach a speaker and how to make this supersonic stuff. Scratching is actually, you have full control with the micropositioner. You move it back and forth, or you rub at the side of one of these trays and suddenly it breaks. It's doable, and I practiced this very reliable in the last time.
Okay.
Thank you, everyone. Please give a warm round of applause to our speakers. Thank you.